And we're live.
We are live.
Excellent. Oh,
Can
you
you
use
tell me
Alacrity
what?
too?
Sorry?
You use Alacrity too? Nice.
Yeah. Actually, I need to not use the full screen thing. We learned that last time. And chat. How do I pop out chat again? Chat.
The YouTube chat? Should be the top 3 bubbles. And then you click pop out chat.
I might need to put OBS over here. Ugh, I can't have. Okay, you're gonna monitor the chat because for some reason OBS doesn't want to pop out chat and be in the background. I don't know why.
Well, I can't. Okay, I can't type in chat. This is stupid. Create a channel to join the chat. What does that even mean? What? How does YouTube work?
All right, let me. Oh, you'll disappear for a second because I'm. No,
Okay.
let me do it. Let me do that from my phone. Tweet. Where's my phone?
Okay. Yes. Hello, Samira. The corgi is in his bed. Ooh, this is a Parca Agent issue?
Yes, this is a Parca Agent issue.
Nice. I have never looked at the Parca Agent code. So I'm excited. Excellent.
Maybe we'll give people a couple of minutes to join.
Sure.
But yeah, I mean, I can talk about it again when other people are here. But basically, what we were seeing is, and I got permission to name the user. So this is from Materialize. They were trying the product, and kind of they're using our suggested resource request and limits of 100 megabytes request and 500 megabytes memory limit. And it was constantly being killed with the 500 megabyte limit. And they increased it. Looks like we've got a new joiner. Hey, Mike. They constantly kept increasing the limit up to 2 gigabytes. And at that point, it stopped kind of getting killed immediately. So very clearly, this was something that happened right at the start of launching Parca Agent on their node. And so I requested them to take a memory profile from the Parca Agent, which conveniently, because it's written in Go, they could do very easily, and then upload it to the pprof.me service that we run. And at first sight, I started looking at in-use bytes, because ultimately that tells us where is the resident memory. But the problem was that after an initial spike, what seems like an initial spike, it did, if we increased the limit to 2 gigabytes, it did eventually kind of become stable. It didn't end up ooming anymore. And so that also means that the in-use bytes were kind of useless at this point, because the problematic memory had already been garbage collected. And so what I thought we should probably do is start to compare the allocated bytes with the in-use bytes, because this is a memory profile that was taken seconds after the Parca agent was started, right? So there's not much difference between the data that has been allocated and the data that has been that is currently still residing in memory. And so the first thing that I wanted us to kind of look into, and we can see that there's really not a lot of memory actually still residing in the process, but a couple of things kind of jump out right at the start. And I feel like it must have to do with something with these two times where we're seeing this package AINUR. I'm not sure if that's supposed to be an acronym or something, but we use this to analyze binaries to figure out what is the version of the compiler or what compiler in the first place was being used to compile this binary. And as we can see by the next frame just underneath, clearly this was a Rust binary where the symbols were not stripped. So Rust version unstripped. And what it does is, and I already have a hunch because I know what this function does, this elf section data function. What it does is it reads an entire elf binary section into memory, the entire section. And so basically what that means is that the amount of memory that we end up allocating in this function depends on how big the binaries are. And we have absolutely no control over how big the binaries may end up being, right? And so that can definitely be problematic. And I have already received the binary that is the primary workload that's running on this machine of the user that was reporting this. And I think we can have a look at it now already. I think you can see if we should increase font size or something, let us know in chat. But whoops. Hopefully this is good enough. The binary is the materialized binary, and as we can see, this is a fairly big binary. And this is, by the way, just the debug infos. This is already the binary excluded and the executable section, which I think is another 200 megabytes or something.
And this is a Rust binary, right?
This is a Rust binary, exactly. Yeah. So I think probably the first thing that we're gonna want to do is have a quick look at this library and see if we rerun exactly what we're experiencing or what we're doing here. Basically, clone the repository of this library and run exactly a test that does exactly this against the binary, and then check the maximum resident memory that we observed while running that test. Hopefully we'll see something, above 500 megabytes or something, which is the thing that would have exceeded the memory limit, therefore caused an kill.
Yep.
I think.
So step one, try to recreate with the unit test.
Exactly. So
Yep.
Let's get started with that. Like I said, I did already have like I said in the issue originally here, I did already have a very quick look at this, and I thought this might happen. So I did already clone that repository. Was it XY proto? All right. So, whoops. Let's just check that we're on latest. All right. So, let's see. This function was rust var unscript, something like that. Yep. That's in the detect.go. Maybe go to detect.test _test. Okay. There are already rust tests. All right, let's take one of these then. Maybe append it to the end. That's rust material. Wow, can't type today. And we'll drop the binary in there. So, copy that binary from to our test data directory. And what did I call the test again? Test rust materialize. So,
Yeah, this materialize. Do you need to change that second string? That's rust nightly. I'm not sure what that label is.
You're exactly right. Yeah, the test immediately failed. So what was that? 167.
Yeah, 167. Not nightly.
Not nightly. Yeah. All right. So we've got our test. And now this is a fun little trick that I actually only learned a couple of weeks ago by one of our colleagues, Javier. He taught me that this built-in time actually, or I didn't realize that this was a built-in. Oops, that was also wrong. Time go test run test rust. So I didn't realize that what I'm running here isn't the time binary. This is actually a built-in in shells. So this is essentially a function that every shell implements, and you actually need to do something like this to actually run the time binary, or you can actually be very explicit about the binary that you're running. And
today I learned.
Sorry?
Said today I learned. I had no idea that wasn't that was built into the shell.
Right? I had no idea either. So yeah. And the reason why I'm why I want to call this time whoops. The reason why I want to call the time binary is where is it? Here. It can actually output the maximum residence size that was observed while the process that it's going to invoke was running. And so that way we can see how much was the maximum heap that our process actually used. And therefore, if this exceeds 500 megabytes, that means that this would actually get an kill with the configuration that the materialized folks reported to us. So let's do that. And all right, we can already see. So this looks like a little
All
bit
right.
over one gigabyte. So I think we're onto something. Actually, what's kind of funky is that this binary, this whole thing is 300 megabytes only, and we read
Are-
a single section into
Is-
memory.
That section compressed? Do they use encoding techniques
That-
there that would
Yeah,
cause
yeah.
this?
So the ELF sections can certainly be compressed. That could definitely be the case. So let's have a quick look at what it is that this function even reads. So here, so we've got Rust version unstripped, and it reads the .debug string. So yeah, this is a section that's not too uncommon to be compressed. So, but let's have a quick look at what this function actually does. So it selects the section, and then it does the thing that we think is the offending thing causing all this memory allocation, and then it searches for Rust marker. What's that? Okay, so essentially in the string section, it searches for a particular string that is Rust-C, that contains Rust-C version. And this is something that you just kind of need to know. This section .debug string, it contains just a giant set of bytes that just basically is a giant blob of null terminated strings. So typically how it works is that from another section in the binary, if you have some sort of debug string that you want to reference, let's say a function name, for example, then an offset into this section is the only thing that the other section will say. So it'll say something like at offset, like this function name is at offset number XYZ, right? And then you need to read the null terminated string within that section. So that's why this actually works, or at least it should. The interesting thing about this Go library that's being used underneath here, or at least it looks like the standard Go. Yeah, this is the standard debug /elf. So debug elf. This is kind of coming from the Go standard library. So what this actually ends up doing, if a section is compressed, it will automatically decompress it when you read it. So you may be onto something here. That would definitely make a lot of sense. I think what we can just do is let's try to recreate what this function does manually against the binary, just to see. So what we can do, we can use a tool called read elf. Yeah, that's what it's called. Muscle memory. I didn't even know what the name of the tool is, but it's read elf, and then you can do a string dump of debug str s data, no, materialize, and then what was it, Rust version, something like that.
Yep.
So if the section is compressed, that should mean that we should not find this, or it would be extremely unlikely that exactly this string occurs in this section.
Mhm.
And if it is compressed, then we need to add um, an additional flag.
So
So
readelf
this,
is not gonna uncompress things by default.
not by default, you need to tell it to attempt to decompress it. Aha. That looks right. So I think you're exact. Yeah, that, I mean, this proves it. This is the compressed section that
If we use
the
the time utility, can we also determine how much memory that the readelf thing uses
yeah,
when
great idea.
uncompressing?
Oops. Yeah.
Just curious to validate if both of them have the same behavior when doing that.
I mean, this looks like it's doing exactly
Yep.
the same
All right.
thing.
Definitely suspect.
Yeah, yeah, yeah. Interesting though. I wouldn't have expected readelf to read absolutely everything into memory. That's that's pretty surprising to me. Anyway, it
Yeah,
seems
if
like
it's a singular section, it kind of makes sense just to default uncompress an entire section at a time rather than pieces.
yeah. But clearly this is not workable for our users, right? So
Right.
we need to figure out a different way to do this, and then hopefully upstream this to this library. As a matter of fact, actually, I want to say we've already done a couple of contributions to this library. Oh yeah, there you go. The person who this is Javier who also told us about the time binary trick. So
Mhm.
yeah, it seems like they're pretty receptive to contributions. So I feel pretty good about um, trying to fix this and then sending a patch upstream to hopefully get it merged. One last thing that we can maybe do is maybe we can write a quick benchmark as well to see how long this thing takes. Just so we have an idea of whether we're making things dramatically worse or, maybe we can make things better even. We're primarily focused on, not ooming after
Yes.
all of this. But it would be nice if we also don't
Make
dramatically
it much
regress
slower.
in performance.
Yep.
All right, then let's get started with that.
Also, whoever named that package is clever. I like it. It's from Lord
What
of the Rings.
is it? What's the
Yeah,
reference?
the Einar, I don't know how to pronounce it. But they're like the first angels or something in Middle Earth,
I see.
if I recall correctly. Maybe they're the elves actually that like become the elves. I don't know. It's been a long time since I've read the Silmarillion, but that would also make sense since it's an elf parser.
It's not what I wanted. Don't optimize. Yeah, exactly. And yeah, we just want to make sure that Go doesn't optimize this whole code path away, which would be extremely fast if we don't do anything. So,
Yes.
all right.
Do you want to explain how that works?
Yeah, so essentially what we're doing here is that we define this variable and we're setting this variable over here. So let's say if we just ran this, there's a chance, and I'm not 100% sure about all the heuristics that the Go compiler runs, but there's a chance that the Go compiler just says, oh, wait a minute, everything in this must examine code path is entirely unused. So I can just optimize this away. This code is useless. But by setting this variable and then using this variable after the loop, we're ensuring that this will definitely never going to be optimized away. That's the idea.
You'd think the Go compiler would not do those optimizations in benchmarks, though. But I guess that's probably a really challenging heuristic to determine.
Yeah, probably. And maybe there may even be, yeah, I don't know. It's probably, I would suspect if it was an easy thing to solve, I would think it would probably be solved.
I'm just an armchair compiler noob, so
okay.
pretending like I understand.
Now we're gonna do our good old benchmark running trick. Here, once again, what we're doing here is essentially you can pass a regex to the go test command to say which tests do you want to run, and this regex basically just matches the empty string, which is totally impossible to have a test that is also the empty string. At the very least, you need to have the tests prefixed with the test keyword, right?
Yep.
So, yeah.
Unfortunately, I always use just 3 X's in a row.
Yeah, there are various things that you could do to ignore this. But basically, what we're doing here is that we're ignoring running tests because I only want to run the benchmark.
Yep.
So, to kind of create our baseline, let's run this a couple of times and save this so that we can then compare it to the result afterwards. And while that's running, we can actually think about how are we going to solve this, right?
Right. Do we know what kind of compression techniques that ELF section uses?
I want to say it's gzip. It's definitely streaming.
Okay.
So we can assume. I want to say everything specified in the standard says that it must be streaming. Make this a bit bigger for folks joining.
I think it's a little too big, but
right. So we've got the section, the data function. I want to say data opens. Yeah, it just called open, and if it is compressed, it's gzip basically. So
okay.
we can assume that it's streaming. So that's good. Since we can use this open function, I think I would roughly design this as like a tail / grep, right? Where we kind of have this streaming buffer, or we may actually need multiple to like window the data that we're reading, and then kind of match if we're finding this string within it. And I think we actually need a window of 2 so that we can kind of read the next one, because what can happen is that the string that we're searching is kind of the one starting at the end of a window, right? So we always need to read a window that is at least larger than the string that we're searching for. Does that make sense?
Right, because the string we're searching for is the Rust-C space version.
And let me look at this again. I think it's actually searching for more afterwards.
Well, it's Rust-C version, and then it would have the version following it, I would imagine.
There's one more character. What is this doing? position 2.
So the bytes marker, position 1, starting 1 past that, position 2. It's looking for the opening of a brace.
So it's rusty version, then the version number, then some open parentheses, right? Actually, what we can do is let's have a look at this string again. Yeah, okay, that makes sense. So we could even say we're taking the rusty version plus the space plus I don't know. Let's be generous, right? Let's say 16 characters or something. And that should be enough of the size of the buffer. But actually, we probably want a buffer much larger than that, because the larger the buffer that we read, the faster the processing is going to be, right? So
Right.
I would still say we probably should make that buffer size configurable, but I feel pretty good about what we just said. The length of the string plus a generous buffer being the minimum.
Yeah. Definitely. The first thing I think of is it makes me wonder if we're going to run into issues in the future, with like the dash nightly, right? So that obviously extends the length of the string. I'm not familiar with Rust, so I don't know how they define their versions. It seems Semver-ish, but then there doesn't seem to be a limit to how large that could technically be once you add metadata.
Let's see
So it
what
almost,
the nightly was here.
yeah, I mean, the easiest way to do it is definitely to like pick a reasonable size and go from there. A more advanced way to do it might be to just have the buffer grow as it matches using like a regex string, right?
Yeah. I do feel if we like let's say we're like super generous and say 1,000 characters. Like,
yeah, no, I'm not saying not go with your approach. I'm just
Yeah.
saying that in the future that might be something to consider is do a more dynamic buffer with the matching regex.
Yeah.
But I think this is fine for sure.
Okay. Then I guess let's kind of start a new file maybe. What do we call it? Like stream reader or something?
Yeah, are we elf stream reader maybe? Although I suppose this is probably going to be more generic than
It's probably
elf, so.
Yeah. I expect it probably. What was the? We get an IO read seeker. So we can probably, if we might be able to make it work with just a regular IO reader. So let's start with that. If we need to expand the interface, we can do that.
Yeah. They don't like lexigraphically sort these strings, do they?
They do not.
Okay.
It's up to the compiler to emit this, and basically anything that ends up still being a null terminated string is fair game. So there's this other thing, I don't think we'll touch on this today, but something called mangling, where in C++ world, for example, the string that you'll find in there isn't actually the function name.
Right.
It's for the better, I'm not sure exactly how to describe it, but it's essentially compression on the function name. I think very specific compression that's done on the function name.
I thought mangling in C++ was to prevent function names from colliding.
It does that as well, because mangling includes the function parameters. So yeah, it does that as well. All right.
Yeah, I only asked because I was curious if there was any techniques we could use for searching for this string. Right. If they're sorted, we could binary search or what have you.
Yeah.
No
That would be
such luck.
nice, but unfortunately not at all. Let's see. How is this gonna work? Maybe we can have something like um maybe like a next function or something that reads the next. I don't know what's in here. This is garbage. But
Read the next buffer.
read the next buffer essentially, and it's up to the caller to decide whether we continue to read the stream or not.
So do we provide the next function like a iterator function inside the parameters? Where it can operate on the bytes?
I think if we do something like this, where the caller kind of decides what to do with this byte slice. Does that make sense?
Sure. Yep.
I don't know yet if this will make sense, but hopefully
That's fine.
hopefully it will. And then we'll need a buffer. And we said something like, what is this doing? This doesn't look right.
Don't trust the AI.
So I feel like if we do this thing where we have the two halves, right? That means that we should only ever read half of the byte buffer, because we need to rotate the last thing that we read into the first half, let's say. So maybe we can actually do the no. I want to be able to return everything as one byte buffer. So
okay.
So I want to do something like copy. Yeah, but basically the length of our buff divided by 2. And copy this into the beginning, and then we read from there onwards. Yeah, something like this. But there was something about the read interface that we need to remember here, right? Read is allowed to not return the full buffer. Is that right?
Correct. You should be able to, technically, it can return less bytes than you requested. And in theory, you should be able to request another read.
So we want to do something like left to read.
Does the IOUtil read all function handle that? Trying to remember if you can just leverage that.
Which one is that?
IOUtil.
You mean
No,
read
never
all?
mind.
No.
Nah, it's not going to do it. Never mind. Oh, it's deprecated. Oh, that's right. They moved it to IO. Old habits die hard.
We'll actually need to make sure. Oops, 1 second. Buffer size. This needs to be divisible by 2, right? Otherwise Otherwise, the copying will kind of go haywire, right? Otherwise, we need to adjust for that one additional byte.
Are you using, this is GitHub Copilot, right? That's giving you
that's
your
right. Yeah.
AI suggestions.
We were talking about this last week on the stream that it's basically you still. What's interesting is you like if you just let it write code, it just produces complete garbage. But if you start typing something and you already know what you want, essentially it's just a really good autocompletion, right? And here it did the right thing, right? I already knew what I was going to type here. I wanted to do exactly this.
Yep. I've definitely taken a block of code it's given me before where it looked like exactly what I was going to type, but there was a subtle bug in it, and it ended up causing me some time debugging it because I trusted it when I shouldn't have.
Yeah, so the thing that it's generated on more than one occasion, and I've blindly accepted it on more than one occasion, is something like this, where we have like buffer, let's say this, right? And then subsequently it does something like append buffer something, like, right? Where my intention was that I actually wanted to do this, right? But it did both generate a buffer that already has length of buffer size and append, where usually we just use that to pre-allocate for the appends to not cause additional allocations. So yeah, still, unfortunately, we still need to think.
Yes. From the chat, we've got a Chat GPT would have written this by now. Thank you, Brandon. I did see yesterday that Chat GPT now has an NVim plugin. So
does it?
Yeah, I don't know how well it does with code. So that would be an interesting thing to face off on. Is it better than Copilot?
Yeah. I was just thinking maybe we need to calculate the length by subtracting the half, but actually since we've just made sure that the buffer is always divisible by 2, actually this is going to give us the correct result. But now we want something, we want a loop that makes sure that we've read the full buffer length. So hopefully we'll always get this on the first read in this for loop, but we can't be sure. So we want half of that, and then left read is also half, and so we want to read no.
So the only time I've actually run into the read operator not returning all the bytes you requested is from Google's implementation of their like S3 API for GCS.
Yeah.
All the other cloud providers actually block until it fills the buffer, whereas they actually adhere to this API.
Yeah. I just want to make sure that whatever we contribute to this.
No, absolutely, it should be correct based on the API. I was just commenting that.
But yeah, it is a very, very odd thing of the reader API. It's definitely something that caught me off guard when we ran into this, exactly from what you mentioned.
Yep.
All right. So actually, what we want is number red bytes. Yes, I think this is how we want it. So we want half plus red bytes. This is how much we want to read. What does this say? Missing comma. Ah, plus buff.
That's not a buffer or a
Yeah.
slice.
And this is r.buff. All right. So first of all, if we have an error, we return. However, if this is an EOF, is there a chance that we do something weird? Okay, no, actually we return the byte slice, so we control we ultimately control how much we return within this. So if this is, sorry, what were you saying?
Nothing. You're good.
Okay. If this is EOF, then we want to return EOF. I need to look at this interface. Look at it here.
Which interface?
The reader interface. So
you would just return our current offset plus n if we hit EOF.
Okay.
Right, because if it's 0 EOF, that's fine. We would just the n that we're adding.
So
would
that
just be
means
0.
that we still need to do read bytes plus n, and then yeah, exactly this. Whereas otherwise, once we've done read bytes and read bytes is half, then we return the buffer. Does this look right?
Yes. 6 in.
I think it does. Okay, so let's maybe.
You might want to throw a comment on the top of next why it's reading half buffers. So that when we come back and look at it in 5 minutes, we're not confused too.
This probably should still return EOF as well, right?
Yeah, that'd be a good signal that we're done.
Yeah. What is it doing?
The autocomplete comments are on fire.
The reason for reading half is so that we can build something like hail file prep something.
Ooh, IO read full. Interesting.
Where something may be between two reads. All right, so let's test that then. So go.
Yeah, I think I just saw the IO read full suggestion from Copilot, and that might actually be a good replacement for this for loop.
What is the
IO read full?
io.read full?
Yeah. It basically takes the reader and makes sure to fill the buffer. Yeah, read full right there.
The error is EOF only if no bytes were read. Okay.
Mm-hmm.
Okay.
So I think we can simplify this.
Yeah. So, okay. What was it? io.read full r dot buff. I know the first one was r, right?
Yeah, it's the reader and then it's the buffer.
And then we don't need to keep track of that.
We shouldn't need this in a for loop, right?
And what does it say? It returns
The number of bytes copied
okay.
and an error if fewer bytes were read.
So now we don't need this weird construct here because it will only return EOF if no bytes were read and it's EOF, right?
Yes, with the one caveat that read full returns error unexpected EOF if reading some but not all the bytes. And since we don't know the exact size, that's a case we should probably handle.
Okay, so that does mean that we may still have this case. But okay. We'll take care of this in a second.
Yeah, but that's an error we can swallow because it's fine. But it does simplify the code quite a bit.
Yeah, it does. It does. We should still, yeah, I think, is this the right thing to do? Let's see.
So on EOF, that means it read 0 bytes. So that's the case where we've basically read up until the end already, and then another next is called. So on EOF,
so if we don't read, if n is not half, do we still get an IO EOF?
No. So if we're reading less than the total bytes that we're requesting, we'll get an IO error unexpected EOF.
So, okay. So here, and I expected EOF like that.
I think it's ERR in front of it as well. The front of the string. Yeah. That's according to the docs. And that means we would return the partial buffer.
Yes, exactly. In this case, we return the partial buffer with no error. And
but we should probably still return an IO EOF, right? So that they can determine.
I think like it wouldn't hurt to call next one more time and then we just get nothing, right?
Okay. Yeah, that's fair. That's fair. Then we return nothing and an IO EOF.
Yeah. Okay, cool. Then let's do some testing of this. So we've got a buffer. Let's make this a bit more interesting. Not hello world. Let's do
not hello world.
Now let's do something A, B, 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 C, 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 C. And then
Just hit your UB key and have it fill it in.
and then we'll say that our buffer is of size 6, but we want to, no, actually of size 3, and then we want to be able to find the 4 B's within this stream, right?
Okay.
So we've got to, I don't know, if we pass 6, yeah, that's what we're looking for. So for then next EOF. What I think the package was using some error helpers. What is this? Assert. Okay.
Is it not using require?
No, it's something else. Assert.
Oh, it's the assert package.
And use this.
Oh, that's a different assert. Yeah, I've never seen this one.
If I've ever used this, I haven't used it in a very long time. How does this work? Okay. Fairly minimal. So I guess it's just that we want it to equal nil, right? I'm guessing that's how this is being used.
Seems to be.
Okay, this
Though it does seem odd that they wouldn't have a no error.
Yeah. But it seems like that's what we're working with. I'm sure if the maintainer has some thoughts on this, that they'll let us know on a PR review.
Yeah.
So what we ultimately want to do is we want to do the bytes.index and
what's the bytes.index function? I'm unfamiliar with that.
That we saw this earlier in the Rust function. Basically, what this does is it searches for the second byte slice that you're passing in the first one. And so if it's -1, that means we haven't found it. If it's anything else, then it means we found it at that index. So if this is unequaled, I don't know what it's trying to do there, but what we want to know is if this was found, and we're going to assume we haven't, but if we find this, then it's been found, and we want to make sure that this happens, right?
Yep, looks good.
All right, cool. Seems like that works. So now the next thing that we're gonna want to do is actually let's commit this for a second. We want to make some nice commits for this person. Probably this additional test that we added. This is a 350 megabyte binary. We probably don't want to commit this to the to the repository.
No, probably not.
So let's just
we can validate that on our side, but use the ones they already have
to
look for the strings that are already exist.
But we'll add a new let's Reduce heat. Stream reader is something that could be used to search for strings, or not strings. Search in streaming. I guess we can actually use exactly that as the struct comment as well. All right. Let's add you as a co. How does that work again? Cool. Co-authored by. What do you go by? Oh, I can't hear you.
It's because my children are having a play date and they're screaming down here for fun. So I muted myself. Yeah, you could just do Thor Hansen.
And what email do you use on GitHub?
We can do me@thor-hansen.com.
Like that?
Yep.
All right, cool.
You got it.
That looks good. All right, cool. Now let's integrate this, I guess, into our detect function.
Yes.
What do we call it? Rust for unstripped is the one that we saw being problematic. Okay, so
Yes, we want to get rid of the section data.
yes, instead of section data, we want to do section open. And what does this return? It just returns the reader. So
Yeah, just a reader, no error.
No error here yet. Then we will have our streaming reader. So move stream reader R, and let's just start with 4 kilobytes. It
Makes
just
sense.
returns an error now though.
Don't we pass it a buffer, not a... I forgot the interface.
No, we wanted to
That's right.
ensure
No,
that this buffer is always. I mean, we could do it the other way around as well. Then we're not doing an allocation here.
Yeah, I think it's fine.
I feel like
I think
it's
it's fine the way it
probably
is. I just
an
forgot what we
API that's
decided.
not. Yeah. An error can only ever happen if this is not even. So I feel like we've done a grave mistake if this error, if an error returns here, right? What do you think of putting a panic here?
I don't believe in panics.
So you think the problem is that this thing doesn't
This
return an error?
true. All right, I'll allow it.
We can see if there's the opportunity to maybe add an error to the function.
Yeah, I think
Signature.
leaving it as is for now is acceptable.
All right, so let's call this buffer size. No. And we write our for loop for buff. Not read, it's next. And error is null and UF. Then we break. Otherwise, we just return. That was what happens otherwise in this thing. Like if we ever run into something, we just return. I suppose that's what we could do here as well. It seems like that's...
Yeah.
I'm not a huge fan of any of this, but I think
we'll the API should probably be returned to return an error.
Yeah. All right. So now we can do pretty much this in this loop. Now
Chat asked to see a corgi, so I'm gonna show one on camera.
If we said we wanted a margin, right? We wanted like a margin of something just completely ridiculous, right? 1024 characters. So
yeah,
that means that we want at least 1024 characters from the point where we're finding the rust marker to the end. Right? Let's say we find it even here. We want to make sure that position is buffer size minus position is it larger or smaller than margin? Buffer size, position. We want it to be larger than margin. No, I see what it was doing. If it's smaller than margin, we want to continue. We want to read the next one. So all right. This seems like it's it, doesn't it?
I believe so. Yeah, this seems reasonable.
Okay, it's missing a return here, but that's it. All right, what was that? Looks like it works.
All right.
And now for our benchmark, let's see if how dramatically worse we've made this. I mean, it should
I don't think it should be much worse. If anything, it should be maybe even better.
I mean, intuitively, if the string, let's assume absolute worst case, right? Like if the string is at the very end,
yeah,
we need to read everything in 2 kilobyte chunks. Actually, that probably means we should make this 8 kilobytes, because that means that all of our reads are 4 kilobytes, which is typically what the operating system does anyway.
Right.
And so, yeah, we can change that though. But intuitively, you know, if the what did readelf tell us earlier? What position
That's a
is
good
this?
question.
Okay, so this means at like position, I don't know, what is F? 16. So
Yeah.
at byte number 16, that's where the string is. So we should actually be significantly faster because we stop immediately when we find this. So let's see if that's true. Okay. Yeah, that's good news.
That is good news.
And
Wow.
that's that's actually amazing. We weren't even looking to improve runtime performance of this, but
2.8 gigs versus 0.01.
yeah.
Wow.
So that already looks like we're gonna be having that saving that we want, but let's make sure that we see the same thing here. Yeah, we're definitely. But 78 megabytes. Where's that coming from? That's still way larger than I thought it should be.
That is extremely large compared to what I would think.
Let's have a look at the memory profile. We've got a memory profile. I can upload it. What's the... Aha, it's other code paths. It looks like it. Oh wait, this is the object. Yeah.
OCaml.
So it's Go version and OCaml version. Let's see if we can improve those as well. Maybe we can do exactly the same thing.
Yeah, I wonder if they're using the same code paths.
So what was it? Go ver. So it does not read the debug string section, but it reads the read-only data section of the binary. So
right.
It's actually that's good. So initially, one other thing that I was thinking about that we could do is we could just read all strings as their null terminated strings, right? And then do the matching on that. That would also work, but now that we've done this like window matching, we can still actually use this here because we can't rely on null terminated strings being available in this. So that's good news. Accidentally did something useful there. Let's see though what else happens in here. So we do a Go version regex. What does that look like? So it's Go and then a bunch of numbers, then a dot, a bunch of numbers, then a dot, and then a bunch of numbers. I feel like if we're doing the same thing as what we were doing before, we're probably good. Like if we read the 8 kilobyte
yeah,
buffer. Actually, let's fix that first before we go on. Rust ver. What is that? 8,192? Is that right?
Put me on the spot. It feels like it's right. 8192. I think that's okay.
What is it? 2 to the power of 15? Oops, no, not that much. 11, 12, 13. Okay. 8,192. All right, cool.
And that
I think
caret operator is not the power operator in Go.
Yeah. Actually, let's talk about that for a second. So we've definitely made the mistake of doing this, And this does not do what we intuitively think in Go. This is, what was it again? It's like some sort of
It's like the XOR operator
bit.
or something,
It's
or
like a
bitwise.
bitwise operation or something like that, right?
Yeah. Yep.
Um, and so this does not
Will not get you what you
equal
want.
1,900 8,192. I forget what the result is, but it's not that.
No.
Anyway, let's try to do the same thing here then.
Why was the code doing a Go version call? Wasn't the unit test just doing the Rust version unstripped?
That is a good question. Why is it even doing that?
Like, I fully believe that this can be optimized in the same way, but I
Rust examiner
thought
of open compiler. Okay. So what it does is, okay, and that's representative of how we would end up using it. So that's actually a good thing.
is it's just trying to figure out what type of file it is.
Exactly. We throw some random binary that we found on a host into this function, and we want to know what compiler was it created with. And
Yeah.
so naturally we need to loop through all of them. And I'm guessing, what we should see if we look through this list now, we should see that Go and OCaml are coming before Rust, right? Because once we found a result, that's what it says here. Once we found a non-empty string, we just return that one. So I'm guessing it's probably either Go OCaml Rust or OCaml Go Rust. Let's see if we're right. Go OCaml PHC version. Interesting. Why? Aha, okay. Because this comment section is probably so small. If maybe it doesn't even exist in
Yeah, it
this.
probably doesn't even exist.
Probably
Otherwise, I
doesn't
think
even
we'd see
exist,
it.
yeah. So yeah, that's probably it. All right, that kind of confirms all of our theories, so that's good. Let's go back to that.
But it does make me wonder if everything under Rust version unstripped should also be optimized.
Yeah, that makes sense. Well, we can have a look at that after this, I would say. Good idea though. All right. Rust. This doesn't give us the index, it gives us directly the, what is this regex again? So this gives us the match, I guess? Right? So this gives us all of this. Yeah, because what it then uses is Go version, all the matches from 2 and onwards. So wait, doesn't regex allow us to get the index as well? I feel like there's something like that.
I feel like there should be, yeah.
Let's open the find all index. But actually, can we find just the first index?
Is it find string index or find index probably then?
Returns a two-element slice of integers defining the location of the leftmost match in B. So the leftmost. Okay, yeah, I think that's what we're looking for, right?
Yeah.
Okay, so go version index. Already know. Wait, go marker? Is that a thing?
According to Copilot, it is.
No, it's not.
It's like, well, you've got a Rust marker, so you probably have a Go
Yeah.
marker.
Go version regex. Yeah, find index. That's what we're looking for. And what was the API? Returns nil. No match. Okay, so
Yeah.
if nil, we continue. Oops. And if go, whoops, go version. Yeah, actually, that's exactly what we want. Thank you, Copilot. Then we continue. And otherwise, I guess we can keep this. This should be pretty cheap once we've determined
Right.
this.
That's a pretty small match.
Yeah. That's probably the same. This one. Okay. I guess we should just run all tests. I would think that there's a go test somewhere. Maybe let's verify that real quick.
One would hope, but yeah.
Test. Oops, go. Whoops, there's no go. No go.
That's surprising.
How do we know that we're not breaking this now?
Big yikes. I guess compile the test as a binary and then try it against that.
Which we've actually already done. We've got the
Right.
anar.test. This is go though. We should just wait, there's a make file. There's a make file in here as well. Let's see if there's anything here. All right, let's do go. Go. Go build. We want an ELF binary, so we need to make sure actually that we are on Go OS Linux, because on I forget what the format is called on like Darwin, which I'm on. It's like Macho or something like that. MACHO, I think something like that. So let's do that, and then just let's make sure also we're on. That's what most of our users are on, so let's test it for that.
Yep.
And we want to output go store hello. And this is go hello. And add it to the all target as well. Go underscore hello. Oops. Because we haven't created the main.go. Right, there you go. No, not that. Just that. All right. Is this just checked in? Okay. Seems like we'll keep this checked in. All right.
Yeah.
Let's add a test for Go then. Test Go. Go. And just to make sure, we should get something out. I'm on the Go version. Go 20.1. So that's what we should get as the output. I just want to see that the test fails. Yep, Go 1.20.1. Go 1.20.1. Now it should pass. All right, cool.
Excellent.
And now we should see if we run our
benchmark. Yeah.
We had our mem profile here.
We expect OCaml to still use up a large portion.
Did that increase?
Yeah, that's worse. It was like 77 before, I thought.
Huh. All right, but looks like only OCaml. Let's apply the same thing and see if it still happens.
Yep. It's weird that it got bigger, but
that is weird.
Whatever.
Maybe
that metric just isn't 100% accurate.
Yeah, it could be. I'm not even sure how it measures that. It might
Right.
be a sampling interval, right? And it might just catch it perfectly where it's still garbage collecting or something like that.
Right.
Okay, so last one, or maybe not last one, but we'll see. Camel version.
Also the read-only data.
Okay, so this works with the marker again.
Yep.
Yeah, you're right. Read-only data. I didn't even look at that. So I think maybe we should convert this into the thing that the Rust one was using.
Yes.
To just see.
Seems like we should be able to.
Yeah. Actually, I think it would even work like this. Since we do this regex afterwards, if we just say, no, we need the index, of course, because we need to know at what position within the buffer it is.
Right.
Okay, so for let's read this part again. No marker. If it's here, we're not going to cut it, so we're quickly just call it position. We don't need this, and we want to make sure the same thing's the case.
We don't want to return if position is -1, right? Don't we want to continue?
Oh, you're absolutely right. That was incorrect over here already.
Yeah. It's just that we found it right away.
Yeah. Nice catch. Okay. I feel like we should probably comment this margin thing. This would seem pretty magic to me if I read this again in a couple of months. But first, That's unchanged, isn't it?
Yeah. That is strange.
Yeah, it does that when there's no data in the profile. Okay, so that's interesting. Yeah, there's nothing in this profile. That's a nifty little trick to read the profile in case anybody's interested in this. Basically, what we're doing is I have the proto definition for the pprof locally on my machine, and I'm decoding the profile and decompressing it, and then printing it to standard out so that we can see what's in here. But as we can see, it has a bunch of sample types defined and a mapping. But what we would usually want to see here is samples, but there's no samples. So this strikes me as something else must be doing these allocations and not our code. So that may actually have already been the case before the OCaml improvement. Anyway, probably still a good idea to have improved this. I just want to make sure that we didn't make the same mistake in the Go version. Did we? Okay, yeah. Here we did it correctly. We continue.
Okay. We may also want to circle around to the other language version functions as well.
What was it called? Compiler version functions. Okay, so Rust for script. Yeah, this looks like it's going to be exactly the same spiel. Check it. I don't know what this is. I hope they knew what they were doing. I'm sure they did. It seems like one of those things, you probably had some sort of regression why you added this.
It's just checking if it exists. I'll be right back 1 second.
Yeah, no worries. We got any questions in chat so far? Not currently. All right, then I guess we can do exactly the same thing here again. Just push its integral. So I just want to check out what do these others do. Didn't string. Okay, yeah, this could be potentially large as well. GCC comment. That's probably okay. Readability might be more important here. Pass. What's the pass?
And we're back. All right. So did we adjust the Rust version stripped? Is that what we're doing right now?
Not yet. I was actually interested in just seeing what's going to be ahead of us, and I was checking out all these other ones, and this one's going to read a new section that we haven't seen yet, but this is essentially yet another string section. So
Yep.
this is going to be the same thing. I feel like here it's probably not worth doing. The comment section tends to be extremely small, just a few kilobytes at most.
Okay.
I feel like readability is more important here. That's already a pretty complex function.
Yeah, yikes.
I don't know what PAS is. FPC? What is that compiler? Have you ever heard of this?
No, but I'll Google it. FPC compiler. Pascal.
Wow. Pascal. Okay. Okay, that makes sense now. PAS. Data section. I'm not actually 100% sure, so probably we're gonna want to do the same thing there.
Seems-
and TCC.
Yeah, it seems safe to do.
TCC usually has this section. Okay, this actually does not even an allocation or anything. It just checks if these sections exist. Okay, cool.
Nice.
So in most of these, that means we need to do some work. We need to do something in these two and in this one. So we've got three ahead of us.
Okay.
All right, let's take our Rust one. We open our section. Here we're going to need to do exactly the thing that we just done for which compiler was it? GHC or something? I forget. The one where it also used bytes.contains initially.
Yeah, I don't remember. I think it was GHC.
And we do position. What do we do? Oh, this is actually kind of funny. We first check if it contains rustc.
Mm-hmm.
Now, if it
Old
does
strip
not
needs to be-
contain rustc, look for the rust marker that may appear in old stripped executables. No, rust marker is probably not created with the Rust compiler. Rust may use GCC for linking. Okay. And there it might go for the GCC version. Okay. Okay. I guess we can still do all of this. Hold on though. The second search, I feel like we may need to do two searches here actually.
Yeah, since we're stream reading it instead of just searching the entire set. I think we could do both of the searches at the same time, though.
That is true.
And then do the logic that it's doing below it based on those things.
Yep. That makes sense. All right. We want to check if bytes.index. No, we don't want to search for the Rust marker. We want to search for /rust c dash. And if I guess
So
we
maybe
can do actually the same thing then, no?
What do you mean the same thing as what?
We can if position, like if we haven't found this index, we search for we can reuse this thing and we search for, what is it, __ rust _
Isn't that assuming that this _ rust thing comes after rust C, which I don't know if that's true or not. Right? Doesn't the ordering kind of matter here because of how we're searching with the stream reader?
Hold on. This says if it doesn't contain it,
Mm-hmm.
and that's what we're doing here as well, right? If it doesn't contain it, we search for this.
Yes, but we're doing a bytes index of just a part of the buffer now, whereas that was checking, is it contained in the section at all? So if we wanted an equivalent, we would write one for loop that checks for rust C. And then if that returns nothing, then we would do another for loop that checks for _ rust. No? Because then it's reading the whole section.
Yeah, I see what you mean. How would we write that into a single for loop?
Yeah, it's kind of interesting because it's not looking for a thing. It's looking for the absence of a thing.
Yeah. I mean, my gut feeling says that we should probably go for the thing that we understand how to write, and if we, after all of these patches, continue to see this being a problem, or maybe we see CPU cycles being a problem, then we can go back and optimize this again. But sure. I think for now I would optimize for writing the correct code.
Yeah. Doesn't matter if it's fast, if it's wrong.
Exactly. Okay, so if we haven't found it, we continue. That's correct.
Mm-hmm.
But if we have found it,
then we would jump to the end section and not do the second search.
Then
alternatively, couldn't we just invert this? Where if we find _ rust, then we want to see if we also find /rust C.
I'm not sure.
We can continue down the path that we know that will work. It's fine.
We don't actually do any matching here, right? So we can just go straight and continue with all of this, right? There's no reading of the version happening here.
Mm-hmm.
It's actually just kind of trying to assert, is this rust or is this not rust?
Right.
And we've got a read seeker. So we want to seek back to the start.
Good call.
There's this nice constant.
Can we ever hit line 284? If this is because we're trying to find the absence of rust C, right? And if it's not there, it's going to continue to hit continue. and then eventually EOF and break out of the for loop, and we won't return Rust, right?
That's correct, though, right? If we
No,
cannot...
because if it doesn't contain Rust C, all right, that's when we want to search. So if it does contain Rust C is when we want to turn Rust. Okay.
Yeah.
All right.
Yeah.
I'm sorry.
But wait a sec. But if it doesn't happen to go into this if branch, we still end up returning Rust.
Correct.
That doesn't seem right. Is there any combination here that we don't return Rust?
Yeah, if it doesn't contain Rust C but does and it doesn't contain the underscore Rust, then it would drop into both if statements.
I guess I haven't really looked at what this if statement does.
It's checking if underscore Rust is present.
-1 is unequal to 0. Aha. So if it's not present, that's the first one, right?
Yep.
Or the previous byte is unequal to 0? I don't understand this.
I don't either, but we shouldn't change it.
I agree.
My guess is underscore Rust is a suffix to something. And so if it's the beginning of
Yeah, you're probably right.
the thing, then it can't be that. It's probably an innocuous check, but it's probably also safe to do.
Yeah. Whoops. That was not intentional. So now we're at the point where we have not found Rust C in the entire stream. So we start the stream over. And we need to invert this second one. First of all, let me move this to up here.
Yes, we do need to invert.
And then let's remove this if.
Excuse me.
So what's the inverse of this, right? That's what we're looking for. So
right.
If it's larger than 0.
Yeah, if it's greater than 0 and is the next one, and then that equals 0. You just flip everything.
It equals 0.
Yep.
Yeah. So then we run this. Oops, I don't want to keep that comment. Then we run this, and that's what we're looking for, right?
Yes.
And GCC version, what was that again? That was the complicated one that just reads the comment section. Okay.
Yeah.
Okay, this seems right then.
Okay.
So let's move on to the next one, I guess.
Mm-hmm.
All right.
Which was what? Was it Pascal?
What's this margin? Margin's not used. Why is that? Because in this case, it's just we're looking for the full string match.
Right.
Okay, that's all right then. We don't need margin here. Let's look for Rust var script beginning. Copy this beginning and D version. Interesting. They have a pretty complete set of compiler support, I would say.
Yeah.
Definitely wouldn't have started with all of these. So again, we won't need margin here because all we're doing is finding if the underscore DMD underscore marker exists. So yeah, that's exactly what we want to do.
Yep.
And actually, we can use exactly this. Cool. Right. Oh, we've got a double. Cool. That's good then. Now, what was the next one? Let's just search for this thing. Oops. GCC we looked at and Pascal, and then I think we're done, right?
Julian had a good comment in the chat that the __ Rust might be checking for the start of a null terminated string. I think he's probably more correct than my guess.
That's why 0 being the preceding byte makes perfect sense.
Yep.
Thanks, Julian. That makes perfect sense. All right. Whoops. So now we are we're gonna need to do the find index thing again. Yeah. So we do first we check. We continue or I guess if we found what is this regex match? It searches for FPC space, then a number, or potentially a number, then potentially more numbers, and therefore at least some numbers. Okay, and then okay, that's do we run into the potential problem here that we could get something like FPC 1 and that matches and that would be at the very end of the buffer, and
yeah,
the regex still matches.
It does seem that way. Because what's the question mark matcher in Go?
This is it can be present or not, right?
Yeah, it's 0 or more.
Yeah. or it's not zero or more, just like yes or no. Like it doesn't matter. It could be there, it could not be there. We'll match either way.
Oh yeah, yeah.
And this one as well.
Hmm.
That's a tough one.
Maybe we leave this function untouched then.
What does the
So
data
that
section contain anyway?
isn't that where they put constants and such?
Maybe someone in chat knows. Where global tables, variables, etc. live. I guess we don't really have any control over this. It could be really a lot, it could be really small, right?
Right. I mean, ideally, we would want to process it more efficiently, but since it's could be very large. But yeah, that regex matching string is challenging with a streaming reader.
Yeah. Yeah, that's a tough one. It's If it's at the very end, we're okay. It's really just the problem when it's somewhere in the middle where two
Right.
But wait, couldn't we then say if the very end we could add another regex here that Pascal version at the end regex that just matches this one. No, that would still do that.
I'm not following.
Oh no, but so I think I have an idea. So whoops, where's my cursor? Here. If we check what it matched and at what index it matched it, and the index is the length of the match away from the end, then we read onwards to the next one.
Yes.
Because then we potentially are at the end and are cutting it off. But yeah, that should work. Whew.
Yeah. Yep. No, I agree. That makes sense.
So we found an index. Cool. And this even does what we want. If the beginning, if This is different. So if index is 0 is equal to buffer size minus length of the length would be the second index. So indexes one, yeah, like that.
Yeah.
If that's what it is, then we continue. And if not, then we return this.
Yeah.
Yeah.
That looks correct.
All right, cool. Didn't expect that on the, is it the last one? Yeah, this one doesn't need anything more. Didn't expect that the last one would be so tough again. Cool. Let's make sure that any of what we just did actually still works.
Yep.
Cool. It looks like it does. All tests pass.
All right. Do we want to run the benchmark one more time just to make sure?
Yeah. Let's do it. Yep. Oh, wow. Can you see a new change? We previously had...
Yeah, minus 100.
Yeah,
it was used to be 0.02, I believe.
Are there actually...
Or
I don't
0.01.
see that. Are there actually 0 allocations now? Oh, no. It's just comparatively very small.
It's just incredibly small.
That's good though. We've gone from what were the old allocations? Oh my. All right, cool. Looks like we've made it both faster and use less heat. That's
excellent.
A good outcome. Okay, so let's clean this up then. And we want to we want to not add... Wait, was there anything in the detect go that we wanted to... Oh yeah, we want to add the go test. Yep, this one, but these we do not want to. What else do we have? The make file. Oops. And was it? Ah, yeah, the go hello world, and then
yeah.
Go. I think that's it. We said we don't want to commit the massive binary, and we'll keep the profiling data around just to be able to open the PR. So maybe we can commit.
Yeah, looks good to me.
So this time, can we do a co-author directly? I'll just copy it from the previous commit.
That's fine.
All right, so what have we done? Use streaming reader to read out sections. Previously we read entire section into memory all at once, and then search the right sense. This is problematic. And the binary, the given binary, we load on critical amount of this patch makes use of the previously produced screen reader to read the out sections and counts. Not only because remove all heap spikes, before I need to go up a bit here. Where were we?
Are you gonna paste the benchmark results?
The original. I want to see the original heap that we saw here. This is what I want. I'll elide the rest here. Not really important. Maybe we should say that we wrote a benchmark with a binary.
Yeah, that's a good call. That we used binary that had a really large. Was the read, not the read only section, whatever section.
To test this, we used a very large Rust binary that was not stripped. Before these changes, we observe a heap of 1 gigabyte. After these changes, we observe a heap of roughly, what is it, 80 megabytes, which is likely just due to. Actually, we can see this probably. Let's have a quick look. How large is the inner? Yeah, so I know this is only 3 megabytes. I still don't know where that comes from, but clearly it's nothing in the Go runtime. We would see something in the heap profiles.
Yeah.
After these changes, we observed a heap of 80 megabytes, which is likely just due to account. Nothing else in profile. Paste the
All right.
result of that as well. What did we do up here?
Remove the Rust mater again.
Okay. Let me just make this clear that this is a command. And then lastly, not only get this, make remove heap spikes, we could also observe massive improvement in runtime speed.
Excellent.
Maybe a quick explanation, likely due to removed applications. All right.
All right. Ship it.
I haven't forked the repo. All right. Let me open a different Chrome. Here we go. Whoops, now I'm removing you. Oh no, there we go. Let's fork this thing. No.
You don't want to origin, you want your remote. Yeah, there you go.
Let me the stream reader. First commit.
Clear, sure.
Fail. All right. I think we're good.
Yep.
Awesome. I mean,
Excellent.
I would say looking at these results, we were pretty successful today, even
Seriously.
though this was really only our goal, right? So pretty happy with that.
Yeah.
Yeah.
That's great.
Awesome. All right,
Very cool.
Do we have anyone else still left in chat? Looks like people got bored around the time when we started writing commit messages. All right, awesome. Yet another super successful stream. I had a lot of fun.
Yeah, that was great.
Glad you
Huge
joined
gains.
me. Yeah. And
Thanks to everyone who watched. Appreciate
yeah.
you tuning in.
See you next time.
We'll see you on Let's Profile next time.
See y'all next time. Bye-bye.